Okay, folks. This leads on from the discussion in the last video about the radical substitution of alkanes. You don't actually have to have watched that before this one, but it will kind of give it a bit of context if you have. So let's dive in to what we're doing here. You can be asked to do a calculation associated with the idea of photodissociation. So the question would be, something like this. What is the longest wavelength of UV light in nanometers that could be used to produce chlorine radicals from a Cl2 molecule? Something technical sounding question. Just as a quick reminder, a little bit of revision of something completely else. Do you remember what is the equation that links energy to the frequency of light? Any memories? We met this certainly when we were back doing the in the elements of life, doing things like atomic emission and absorption spectroscopy. There was an equation linking energy to the frequency of light. So hopefully you remembered that it was E equals HF. So do you remember what the different parts of that equation are and the kind of units that they are in? Take a moment to have a think, and where you get any data that you need to do this calculation. There's a constant involved. What is it? Where would you find it? So you should remember that here the E means energy. That's in joules. Joules are the standard unit of energy. So although in chemistry we might report energy in kilojoules for convenience, because it just gives smaller numbers, when you're dealing with quite large numbers, the standard unit of science is the joule. And so when you're doing a sort of proper science equation like this, not just some little handy figure something out tool in a chemistry lesson, but a kind of one of the proper science equations, then you use standard units. What is it actually the energy of? So it's the energy in joules provided by one photon of light. And that's very important that you get your head around that. Otherwise, you won't really see the process that we're doing when we use this equation in a calculation. So you can think of light traveling in little packets, little particles, carrying a certain amount of energy. How much energy each particle carries depends on the frequency of light. The higher the frequency, the more energy each photon carries. The lower the frequency, the less energy each photon carries. H, did you remember what H was? This is Planck's constant. Probably should have put a capital P there because it's some guy's name. Planck's constant, something that you won't be told in the exam in the question paper, but you're not expected to memorize it either. It's on the data sheet. And it is 6.63 times 10 to the minus 34 joules per hertz. And then F is the frequency of light in hertz. Okay, now there is another equation that you'll need in order to be able to do this calculation, and it's the energy. It's the equation linking the frequency of light to the wavelength of light. So less familiar, but maybe you have it in your head. So the energy linking the frequency of light to the wavelength of that light. So light can be described by its frequency or its wavelength, and there's an equation that lets you convert from one to the other. Do you remember what it is? And it tends to be written like this: C equals lambda, and then this kind of Greek V thing whose name I can't remember, but it doesn't matter. You don't have to call it by its name. So what are the bits of this equation, do you know what those symbols refer to? So the correct answer is that c is the speed of light in a vacuum, which is just normally said as the speed of light. You can slow down light depending on what you make it pass through, but this is the kind of speed of light when it passes through a vacuum. And that's on the data sheet. And it's 3.0 times 10 to the 8 meters per second. Lambda, this lambda symbol then is wavelength. And this being a proper science equation, the units will be the standard science, the standard units for things. So the units is meters for wavelength. And then this symbol, for whatever reason, although we put F in equals E equals HF, you can also use this V symbol. So this is frequency in hertz. Okay, so we've got these two equations, and then we can get asked questions like this. Calculate the longest wavelength of light in nanometers that can photodissociate Cl2. And then it would tell you that the bond strength of Cl2, so the bond strength of the Cl-Cl bond, is 330 kilojoules per mole. So this is the bond enthalpy. Remember, bond enthalpy is the energy required to break 1 mole of a bond in the gas state. Okay, this is going to be a multi-step calculation. You don't have a hope of remembering it if you can't see the kind of point of the journey. So what's crucial here is you don't just try and memorize random actions, but you actually just kind of see the flow of where we're starting from and where we want to head to get some logic from it. And that way you can kind of think it becomes fairly obvious what you need to do next. But this is all fairly technical stuff, so do expect it when you first meet it. Quite possibly, unless you're very mathsy, to be a bit like, what? And then you're going to have to go back over it a few times to make sense of it. Where it says calculate the longest wavelength of light, what's all that about? All that means is that light, the energy supplied by light goes up as the frequency goes up, but goes down as wavelength gets longer. So all it's saying is calculate the wavelength of light that just breaks that bond. Anything shorter than that means higher energy, so that would be fine. It could still break that bond. Anything longer than that, a bigger wavelength, is less energy, so then it won't be able to break the bond. So you can be asked to calculate the minimum frequency needed or the maximum wavelength needed in a way. Yeah. Okay. Right. So we are heading from, our journey is to go from 330 kilojoules per mole all the way to wavelength in nanometers. And so we're going to have to go via E equals HF to convert to frequency. And then we're going to have to go via C equals lambda V to convert to wavelength. However, we are going to have to do a bit more work than that. So have a look at these steps. So step 1, if we start with our 330 kilojoules per mole, this is in kilojoules, but equals HF needs joules. So we can convert. So just pause a moment. How do you convert from kilojoules to joules? What is the factor, and do you multiply or divide by it? So the key thing to remember here is that 1 kilojoule is 1,000 joules, just like 1 kilogram is 1,000 grams, 1 kilometer is 1,000 meters. So each 1 kilojoule is 1,000 joules. So you notice what we're doing is multiplying by 1,000 to get from kilojoules to joules. So 330 times 1,000 is 330,000 joules per mole. Okay, we can't use the equals HF equation unless we're in joules, so we've got to do that. But there's more work, unfortunately, before we can use E equals HF. Step 2, the 330,000 joules per mole is for a whole mole of bonds to break. But each photon only breaks 1 bond. Hopefully that makes sense. Little packet of light energy comes along and hits literally the bonding electrons in a pair of in one bond, the pair of electrons, and excites them in a way that that bond breaks. It can't destroy a whole mole of substance. One little photon of light isn't some kind of nuclear weapon that just causes mass destruction. It just hits one bond and has one effect. So we need to kind of scale down from 1 mole of bonds to 1 bond. So pause for a moment. How do you think you might do that? There's a particular constant that you're going to need here. What might that be? Where would you find it? And so hopefully you've remembered that we use the Avogadro constant. That tells us how many of something there is in a mole. A mole of anything, remember, it might weigh different amounts for different substances, but what actually defines it is that it is simply the Avogadro constant number of formula units of anything. So that is 6.02 times 10 to the 23. And that's on the data sheet. So if we want to scale down from a whole mole to just 1 bond, we're going to take our 330,000 joules that it would take to break a whole mole of bonds and divide by how many bonds there are in that mole of bonds to find out what one mole would take. It looks fancy, but it's actually just sort of everyday, almost primary school maths. If 5 sweets cost 40p, how much does 1 sweet cost? They all cost 40p together. There's 5 of them, you divide by 5. So here, all the bonds together take 330,000 joules to break. So how much does 1 joule take, 1 bond take to break? Well, we divide by how many bonds there are, which in a mole is the Avogadro constant number, the 6.02 times 10 to the 23. This is going to come out as a very small number, so it takes a tiny amount of energy just to break 1 bond. However strong, we might say, that they are. So this works out as 5.482 times 10 to the minus 19 joules to break 1 bond. Okay, the good news is at this point, we can now use E equals HF because we have an amount of energy in joules required to break a single bond, and that is what would be supplied by a single photon with just enough energy to break it. So step 3 is to convert to frequency. So we know how many joules of energy are needed to break the bond, so therefore what frequency of light will break the bond. So we're going to use E equals HF. So if you want to work out frequency, how would that rearrange? Pause and have a little think there. What would that equation be if you rearranged it to be in terms of frequency? Frequency equals, and hopefully you're saying we'll divide both sides by Planck's constant. So frequency is the energy divided by Planck's constant. So in this case, frequency then is the 5.482 times 10 to the minus 19 divided by, from the data sheet, 6.63 times 10 to the minus 34. And things are going to flip round here because where we had a very small number, if we divide by 6.63 times 10 to the minus 34, we now get a big number. I've just messed it up in my calculator. So just give me a moment. 330,000 divided by 6.02 times 10 to the 23 was that. And so divided by 6.63 times 10 to the minus 34 is, don't need that squiggle, is 8.268 times 10 to the 14 hertz. So where our amount of energy was tiny, the frequency is quite big. Those frequencies are quite large numbers for visible and UV light. Okay, have we answered the question yet? No, because the question was to calculate the longest wavelength of light in nanometers that can photodissociate Cl2. At the moment, we've calculated a frequency. So this is actually the smallest frequency of light that can photodissociate Cl2. So step 4 is to convert to wavelength. We weren't asked for frequency, we were asked for wavelength, so convert to wavelength. And so we're going to use C equals lambda V. So if wavelength is the lambda bit, just make sure that you can rearrange that equation to work out wavelength. How does that rearrange? What would you do? What does it look like? And so hopefully you can say, well, we would just need to divide both sides by the frequency, the V symbol. It'll cancel on the right where the wavelength is, and it will appear on the bottom on the other side. So now we can plug our number in. Remember that c is the speed of light, and that's just a constant. That's on the data sheet. So that's 3.0 times 10 to the 8 meters per second from the data sheet. And we've just calculated the wavelength. So this is from the calculation above. So we can say that the longest wavelength that could break that bond then is 3 times 10 to the 8 divided by 8.268 times 10 to the 14. Which is that 3 times 10 to the 8 divided by that answer is 3.628 times 10 to the minus 7. Well, that's nice, but what is the unit? Remember, the C equals lambda v equation is a proper science equation which uses standard units. Wavelength is a distance. The standard unit of distance is meters. So this pops out as meters. Did I put that when I wrote the equation down? Wavelength in meters. Yeah, good. So that's there. So we now have a problem, or we have a little bit of work. Step 5 is just to convert from meters to nanometers, the wavelength. And you might well be sitting there going, well, I don't know, never heard of a nanometer. How am I supposed to know? The answer is you are expected to memorize it. So here's the thing. 1 meter is 1 times 10 to the 9 nanometers, i.e. it's a billion nanometers in a meter. Yeah, 1,000 million, 10 to the 9. That's right. So complicated, right? But there we go. Unfortunately, that's something that you are going to have to remember. So what do we do with this? If we have our thing in meters, then to go from meters to nanometers, we're going from 1 to 1 times 10 to the 9. So we're going up. We're going to have to multiply our meters by that factor. There's more than one way of doing this conversion. So if you can think, well, logically, I would do this a different way, get the same answer, that's fine. So we're going to multiply our meters by 1 times 10 to the 9 to get nanometers. So if we take our 3.628 times 10 to the minus 7 and we multiply it by 1 times 10 to the 9, I shouldn't really need to put this through the calculator, but I will, just to, I don't know, avoid panic in my brain. And that is equal to 362.8 nanometers. And there, at the end of all that, is your final answer. Okay, especially if you're not such a fan of maths, then you might be looking at that going, oh my days, what a nightmare. Can I just reassure you, none of it is actually complex maths, right? It's actually just a multi-step journey, which can seem intimidating, but along the way, we have multiplied by 1,000. We have divided by a number, the Planck's constant, the Avogadro constant, 6.02 times 10 to the 23. We have divided by a number, the Planck's constant, 6.63 times 10 to the minus 34. We've then divided again, the speed of light divided by the frequency we'd worked out, and we've multiplied by a factor, 1 times 10 to the 9. So all we've done is a bunch of fairly simple multiplying and dividing. The maths is not complicated. What's complicated is the logic of all the steps and making sense of that. So just have another quick scan of the journey. We started with this value in kilojoules to break a whole mole of bonds. We know that to cross over to frequency, we need to use E equals HF, and that uses energy in joules and relates just to a single photon that can affect a single bond. So we've got 2 jobs to start with. Step 1 here, and it doesn't matter which order you do these in actually, is to convert from kilojoules to joules, multiplying by 1,000. And step 2 is to scale down. Instead of thinking about a whole mole of bonds breaking, just one bond breaking. So we're going to divide by how many bonds are in a mole, the Avogadro constant. And then once we've got that amount of energy needed to break one bond, we can figure out the frequency needed to break one bond. That would be the minimum frequency that would break the bond. And so to do that, we use the rearranged equals HF, F equals E over H. And so we take the energy needed to break one bond, we divide by Planck's constant, and we get, therefore, the frequency of the light, the smallest frequency that would do the job. And then once we've got frequency, we can just use that relationship between frequency and wavelength to work out the wavelength. So the frequency, the relationship revolves around the speed of light, and we can just rearrange that equation to be able to work out the frequency or the wavelength given the other one. And so having done that, we can convert. So taking the speed of light and dividing by our frequency, we can therefore work out the wavelength, the longest wavelength that would do the job. But that's going to be in meters. So the final thing is to convert to nanometers, and that means multiplying by 1 times 10 to the 9. Okay. You want to practice this, obviously, and rather than just getting you to do exactly the same steps, I will get you to see if you can follow the logic. And again, you know, this is all about having a go and blundering around a bit so your brain can map out the land and start to build skills. So don't worry if you feel I can't do this, I'm just getting it wrong. The journey to being right lies firmly through the land of being wrong. There is no shortcut. You just have to be wrong a lot until your brain has enough experience. So don't panic. So you could get a question like this: calculate the highest bond enthalpy that could be photodissociated by light with wavelength let us go for 341 nanometers. Okay, so this is exactly the same calculation in reverse. So see if you can apply the logic and get there. So pause the video, have a play. When you're ready to check, then come back and see if you're right. Okay, so if you've had a go at that, we are going to work backwards through this. We're in nanometers. To work through to bond enthalpy, which is in energy, we are going to have to turn it into frequency, which we can then put into our E equals HF. But before we can turn it into frequency, we need to be in the right units to use the C equals lambda V equation. So step 1 here is to convert to meters. There are 1 nanometer is 1 times 10 to the minus 9 meters. So we are getting smaller. So we're going to multiply by 1 times 10 to the 9. That's our factor there to get from nanometers to meters. So 341 times 1 times 10 to the minus 9. Actually, maybe that's a confusing way around of putting it. Let's write down what we wrote before. That 1 meter is 1 times 10 to the 9 nanometers. So to get from nanometers down to meters, you're going to be dividing by 1 times 10 to the 9 in order to go from 1 times 10 to the 9 down to 1. So we can take our 341 nanometers and divide by 1 times 10 to the 9. And what we'll get is 3.41 times 10 to the minus 7 meters. So this is the wavelength in meters. The next step then is to convert to frequency. because we've got to be in frequency in order to use the equals HF to work out the energy that the photons could supply, and hence the bond enthalpy of the bond they could break. And so this uses C equals lambda V. So hence we're after frequency. Frequency is C divided by the wavelength. And remember, C is the speed of light in a vacuum. It's on the data sheet, 3 times 10 to the 8, divided by 3.41 times 10 to the minus 7. And so if I plug that in, 3 times 10 to the 8, divided by 3.41 times 10 to the minus 7, comes out that the frequency that wavelength would represent is 8.798. Oops. Times 10 to the 14 hertz. So note we had a frequency like that before. The frequency of kind of UV visible light is definitely up in that sort of territory, 10 to the 14-ish hertz. So look out for that. If you've got something wildly different, i.e. like 10 to the minus 30 or something, or much bigger, 10 to the 50, then you're probably, you're almost certainly wrong. And so you might need to recalculate. So expect those kind of 10 to the 14-ish numbers for frequency. Okay, that's all very well. We're not being asked for frequency. We're being asked for bond enthalpy that could be broken with light of that wavelength. Bond enthalpy is about energy, so we can convert to energy. And to do that, we're going to use E equals HF. We've got the frequency there, and hence, if we look up Planck's constant on the data sheet, we can find that that is the 6.63 times 10 to the minus 34. And then we can multiply that by this frequency. We've found 8.798. Sorry, I've just realized I've written rubbish, times 10 to the minus 34. So 8.798 times 10 to the 14. And so if I multiply that, 6.63 times 10 to the minus 34, we get down, if you remember before, the energy required to break one bond is tiny. So that's 5.833 times 10 to the minus 19 joules. So this is the energy required to break one bond. It's the energy supplied by one photon. So it's going to break one bond. Okay, so we're not ready yet because it asked us for the bond enthalpy of the bond, that the strongest bond effectively that could be photodissociated. Bond enthalpy is always in kilojoules per mole. That's what all of these enthalpies are reported as. So at the moment we're in joules for a single bond. So we have to carry on our little journey. So to break 1 mole of bonds, we would have 1 mole worth of photons hitting the bond in order to break them. So we're going to scale up. And that means we're going to take the energy required to break 1 bond and we're going to multiply by how many bonds there are in a mole, 6.02 times 10 to the 23. So times 6.02, and that's coming out as 351,137. So what have we worked out there? We had an amount in joules to break one bond, and we've scaled up to break a whole mole of bonds. So this is still an energy in joules. We haven't changed that. But this is to break a mole. So it's the joules per mole. And then finally, 5, standard thing to report enthalpy change of any kind in is kilojoules per mole. So we're going to convert to kilojoules. Okay, so there's 1,000 joules in a kilojoule. So we're going from the 1,000 down to the 1. So we're dividing by 1,000. And so 351,137 divided by 1,000 is 351.1, just to give it 4 sig figs, bit random. And this is now kilojoules per mole, because we worked it out as a per mole value and now we've converted to kilojoules, and so that would be the answer. Phew. Okay, that's quite enough for one chunk. We will stop it there.